Hi, I'm Patricia McKenzie, and I'm joined here with Rohit today, and I'm actually in my house, so I'm also joined with my dog Gloria in case you see her, to tell you a little bit about something a lot of your companies have, an object-relational mapping, or ORM. But first, a little bit about me. Like I said, my name's Patricia. I've been at Meta since 2014, and before that, I studied mathematics at the University of Washington. One reason I find ORMs particularly interesting is because they're a core part of your classic data structures class that's still foundational to a lot of applications today. So that's why ORMs are interesting. But what makes Meta's ORM different? Well, beyond just the scale, being one of the hottest code paths in the world, Meta's ORM, the Ent Framework, honors privacy. In this talk, you'll learn about how we built privacy into the framework, how we've increased adoption, and how we've scaled our foundations to support an ever-growing set of use cases. So what kind of use cases or scale are we talking about here? Well, bringing it home a little bit, you might have opened the Facebook app this morning. You might have loaded or seen one of the trillions of photos on the site. Or you might have seen one of the millions of group posts loaded every second. This social network, all of the photos connected to you and your friends or the groups you follow, are all powered by the Ent Framework. So we've talked about the scale, but what is an Ent exactly? Well, the Ent framework is a unified storage-agnostic framework for reliable and efficient interactions with our data. And an individual Ent is an object that represents something in the social graph, like a user, a business, or a photo. Looking a little deeper into that photo example, here's one of those Ents as it exists on the site, and also how it exists to engineers at Meta. On your left, that's what you see on the Facebook app, a collection of photos that I posted from a trip to the Grand Canyon. And on your right, that's what an Ent photo looks like in code, or as an object. In this snippet, you see getters for fields, like the caption, and edges, like the location. That's a brief look at Ents, but here's Rohit now to tell you a little bit more about the architecture.
Cool, thanks Patricia. My name is Rohit Ahuja, and I've been working on the Ent framework for almost 4 years now. Hopefully you have a sense of what Ents are supposed to do. I'd now like to scratch the surface of our framework's architecture. I'll provide a high-level overview of the 3 main components of the framework that allow for consistent application of privacy controls. The first component we'll cover is the Ent class, which is really the fundamental unit of our framework. An Ent is a read-only, privacy-controlled, strongly typed wrapper around data. This is the object in our ORM. In this code, we're loading a photo from storage. Every load that happens through the Ent framework will ask for 2 pieces of information: a viewer context, which represents a user, and the ID of the object that you're loading. You don't get back some dictionary of data as you would from a data store like MySQL. You get an Ent object that you can call typed methods on, like getCaption. I mentioned that these things are read-only, and this is pretty important. You may find in other ORMs that they mix the read and write paths where you can modify this object directly. However, there are some complications with that. You can get away with making invalid changes, and if you're not careful, you can pass these modified objects as though they are valid and cause issues downstream. We want to pass Ents around as though they are valid and have been checked in various ways. Ents allow for enforced privacy controls. Every Ent has a privacy policy. Patricia will go over this later, but an Ent will not be returned if the privacy policy denies the viewer that's trying to load this data. This is the thing that we're most concerned about at the company. Ents are strongly typed because they're object-oriented. Fields are accessed through typed methods like getCaption. We'll talk about how these methods get defined later on. And to optimize for loads, Ents are cached per viewer and ID. We have to be careful with this, so we'll clear caches completely anytime there's a write during a request. And finally, Ents are storage agnostic. The Ent APIs impose a graph-like data model on top of a variety of data stores like Tau, MySQL, key value stores, blob stores, counting services, and so on. The second component we'll cover is NQL, which stands for Ent Query Language. NQL allows you to do efficient, type-safe traversals of the Ent graph. For the photo that we loaded earlier, we use NQL to query the tags in that photo. We can also query for those tags profiles, apply filters, orderings, and so on. NQL provides us with a fluid query builder. You can build your entire query instead of fetching Ents in steps. NQL also has privacy controls. Privacy will be evaluated for each ent or edge that is loaded in a query. Also, NQL is strongly typed. All methods for querying, filtering, and ordering are type-aware, so you can only build valid queries. NQL is composable. Since queries are immutable, they can be passed around and reused in other queries. And finally, NQL is a generic API. The logic for optimizing and executing these queries on the storage backends is hidden, which allows us to transparently leverage indexing systems to optimize queries. I mentioned how the read and write APIs are separate. Ent Mutator, which is our third component, is our API for building, validating, and executing ent creations, updates, and deletions. With a single interface for writes, we can provide developers with the features to execute highly complex mutations for their products. As you see on the right, Ent Mutator looks a bit like NQL in that we can build mutations with strongly typed setter methods and then execute them. We also allow users to apply these things called actions to their mutation, which are higher-level APIs that users define to centralize their mutation logic. During the update, we're calling this method called action add tags, which will add photo tags, perform other relevant mutations, and potentially have its own policies on top of what entphoto already defines. Mutator will honor privacy policies and evaluate a layer of permissions that ensure that you, the viewer context, can perform this write. We also perform data validations. If you wrote to a data store directly, you can write whatever garbage you wanted and none of it has to make sense. Mutator provides an extra layer of validations that ensure that the data people write is meaningful. We'll check that field values are valid, edge targets are the correct type, and the data post-mutation is well-formed. An ent schema is kind of the center of it all. It's where you define the attributes of your ent, its connections or relationships to other ents, and other details like where it'll be stored and whether it allows writes. It's a structured and configurable class that tells us what our data represents and what it's connected to. For our ent photo schema, we've defined a string field for our caption and an edge to the users tagged in a photo. This is what allows us to read and write these things through the ent, entql, and ent mutator. Every ent schema is also verified to ensure that all of its settings are valid and in sync with the storage schema in production. And with this rich definition for data, we code generate all the components that the framework provides, including the 3 mentioned earlier. Our code generation process works by feeding the ent schema into a script called gencode. The script will generate components like the ent mutator, necessary NQL classes, and so on. But why do we need to generate code in the first place? You might have picked up on this already, but we care a lot about type safety. With explicitly generated code, we can type user APIs accurately and prevent all sorts of issues at runtime. Dynamic code would be expensive, unsafe, and hard to debug. Additionally, ent schema defines fields, edges, and configurations that produce interconnected methods across numerous classes. These all need to remain in sync. It would be a developer experience nightmare to rename a field and have to change dozens of associated methods manually. And there was a time when ent schema didn't exist, and so ent and ent mutator had to be written instead of being generated by a script. This meant that the read and write APIs were not only separate, but also inconsistent. Here's a quick timeline on the evolution of our framework. Before ent, our codebase was littered with these raw call sites that fetch data directly from TAL. Checking privacy involved a lot of these if conditions on whether the user can see a loaded object. The lack of type safety also made this code vulnerable to runtime errors as well. In 2010, we introduced ents as an easy way to define and enforce controls over social graph data. Our initial motivation to do this was the desire to control the audience for a user's post. At this time, there was no concept of an ent schema, so we couldn't generate these ents. They had to be written manually. In 2012, we introduced ent mutator to enable complex mutations of the social graph that allow for improved privacy settings. Ent schema came in 2013 to bring structure and order to these disconnected components by allowing us to generate them for the user. In 2015, we introduced NQL as a way to unify our querying approach and enable global optimizations that make our products faster and more reliable. And as our core components came to form, we invested in a multi-year effort to modernize all data models to one have an Ent schema associated to it, and 2, have all queries go through MQL. This is something we completed as a whole in 2021. And finally, this leads to where we are today, scaling privacy for all online data, which Patricia will go over next.
So as Rohit was showing, privacy, or who is viewing the data, is a key piece of the Ent Framework's architecture. But why? Why do we include privacy in this core piece of infrastructure at Meta? And how does it work? And how do we make sure that we are meeting users' privacy expectations, ranging from data retention to visibility, across the entire user experience? Well, it all starts with what we formalized as Meta's philosophy towards privacy. Now, most philosophies are kind of complicated, but this one is pretty simple and has been taking shape since about 2016. Privacy should be easy for non-experts to get right. We have several categories of user expectations that every engineer should feel able to master. Building privacy into core frameworks, such as the Ent Framework, makes it easier to protect user data across all products and services. It also reduces the burden on engineers to learn and define custom privacy solutions that could leave gaps or introduce failure points in user data protection. It forces engineers to think about privacy from the inception of their products. Now, that's cool, but how does privacy actually work at Meta? Rohit mentioned this earlier, but now I'm going to walk you through the key components in the framework that make sure privacy is being evaluated every time someone loads some data. And I'm going to use that example of the photo from earlier. So let's start on the left here and say that the user is you or me, and we're attempting to load that photo of the Grand Canyon from earlier. Well, every user comes with a viewer context that Rohit was mentioning. That tells us who is trying to view the data, as well as any special permissions they might have. In code, this is passed in on entload and abbreviated as VC in the snippet here. We use that viewer context when evaluating the Ent's privacy policy. The privacy policy is generated for every Ent schema and can contain a set of rules ranging from super simple, like allow if I own the object, to pretty complicated, like deny if this is posted in a secret group that the viewer isn't a member of. Each rule can return an allow, a skip, or a deny result. It's pretty self-explanatory. If a deny is returned, the user cannot see the data. And if a skip is returned, we move on to the next rule. If an allow is returned, the user can see the data. The rules are evaluated in order from top to bottom. Once again, let's look at one of these policies in code, the way an engineer at Meta might see it. This policy is made up of privacy rules with specific logic for the particular use case, so photos here. In this example, you see rules like deny if blocked or allow if friends. Those rules each take 2 inputs, the viewer context that we've been talking about, as well as the actual data we're trying to load. That data can be pretty involved. In our photo case, we use the fields and edges associated with a photo, so things like all of the friends of the owners, for example. We use that to make a decision about whether the viewer can load the data. In code, this looks pretty simple, but it's actually a really powerful mechanism to help users control who has access to their data. In the last example, we saw how important privacy evaluation is to loading data. We need to meet our users' privacy expectations around when data can or should be deleted, as well as who can see it, like in the photo example involving blocked users. In order to honor all of these expectations across the entire experience, we need to be consistent and structured in how privacy is evaluated. To do that, we need the data to be standardized. I've only named a couple of these user expectations, but they each involve different ideas around safe data access and reporting. Doing this completely and consistently at our scale is a serious undertaking. So, what kind of scale are we talking about? Well, standardizing all of the data at the company involves over 40,000 unique schemas, and that number has grown by over 10x in just the last 5 years. The number of different storage types we are supporting has grown too, climbing to over 30 different types. By structuring all of the data at Meta, we enable teams to react to these changing requirements faster. They can share privacy rules and policies rather than updating a Mount Everest of calls to loading data, as every day is the photo of the Grand Canyon I loaded this morning. But the scaling doesn't stop with privacy here. I'm going to hand it over to Rohit now to tell you about how we are scaling the framework as a whole, now that there are an even more diverse set of problems and use cases resulting from the massive standardization effort.
So Patricia has mentioned some alarming data points about the scale that a framework needs to handle. The byproduct of this dramatic growth in schemas is making us hit limits in generated code size, memory, runtime, and meeting the support costs of an ever-growing user base. Because of this, we're seeing ripple effects across the company. We're tackling this problem organizationally, with each of our teams having a tight focus on the various scaling challenges across the framework. The platform team focuses on the developer experience by simplifying our APIs and providing our customers with the tools to be self-sufficient in their development. The retrieval team works on the efficiency, safety, and security of NQL. The foundation team makes our larger framework type-safe and efficient in our runtimes and code generation process. And the storage team builds the abstractions that enable our framework to support our growing number of storage backends. We've been able to scale by having different teams work on these various problem areas. The architecture of our framework allows our 4 teams to operate well without disrupting our users. We've had a constant theme of raising the abstraction, which allows us to keep the complex operations of our framework running behind the scenes. Instead, we present users with intuitive, well-documented APIs so that they can be independently productive and distanced from the work we do internally. We've also heavily modularized the internals of our framework, building maintainable abstractions for supporting backend storages, partner integrations, new field and edge types, and so on. This provides us with a separation of concerns because we can operate without stepping on each other's feet. We have a long future of work to further our efforts in privacy and continue to meet the scale of our framework. For example, we're spinning up a new team to evolve privacy policies from a performance and usability perspective. We're raising the abstraction of our framework by automatically choosing the storage backend for developers so that they don't have to. We're working closely with our programming language teams to leverage the new features that allow us to evolve and scale the framework. And finally, we have an ongoing process to modernize our framework by deprecating years of tech debt and onboarding users to safer, more reliable APIs. We're always hiring, so please reach out if you're interested. Thank you for listening to our presentation about the Ent Framework, Meta's Object-Relational Map.